Hello, how are you students? We come back with new lesson in physics grade 10. Speak about lenses and ray diagrams. By the end of this lesson, we must learn distinguish between converging and diverging lenses in terms of shape, light path. Use the terms principal, focus, and focal length. Describe the standard ray by drawing in a ray diagram. Draw ray diagrams for the formation of a real image by single lens. Draw ray diagrams for the formation of image by convex lens. Describe the nature of an image using the terms enlarged, same size, dimensioned, upright, inverted, and real image, virtual image. Draw ray diagrams for the formation of images by concave lenses. Converging and diverging. A converging lens has a double convex lens. It means if we cut this lens from this point and take this part and put up, it will construct diverging lens. Okay, so converging has a double convex lens, focuses parallel to a single point and can form a real image. Incident parallel ray, it will be focuses in a single point. This point is called focus. Diverging lens have a double convex lens. Also, if we cut this lens from this point and take this part put up, it will construct converging lens. So diverging lens have a double concave lens, will always form a virtual image. The anatomy of lenses. Anatomy at a convex mirror, virtual axis. This is a virtual axis. This is a focal length, double focal length. This is a focal length, and this is also a double focal length. Note that there are two foci, one on either side of the lens, and that rather than C, the center of the curvature. We have 2F, it means twice of focal length. Twice of focal length. C is the center of curvature and F is focus. Double F or 2F is double or twice focal length. Refraction rules for converging lens. An incident ray traveling parallel to the principal axis. The principal will refract such as it travels through the focal point on the far side of the lens. This incident ray, it will be refraction and will pass through a focal point. And this also, like this, it will refract and concentrated or pass through a focal point. Incident ray, which travel parallel to the principal axis, will refract through the lens and converging to a point called focal. An incident ray traveling through the focal point will refract such as it travels parallel to the principal axis on the far side of the lens. If the incident ray pass through a focal point, it will be refract and pass parallel in the other side, like this, our principal axis. Point note. Not all converging lenses are double convex lenses. Converging lenses may have different shapes with wrong ray diagrams. Therefore, we ignore the shape of the lens and refract the rays and the line representing the vertical axis. Reflection rules for diverging lens. An incident ray traveling to the principal axis, this is the principal axis, will refract such as its extension travels through a focal, yes, a focal point on the near side of the lenses. Diverging lens is said to have a negative focal length, since rays which enter the lenses traveling parallel to the principal axis diverge. A diverging lens is said to have a negative focal refraction rules for diverging lens also. An incident ray traveling towards the focal point on the far side of the lens will refract such that it travels parallel to the principal axis of the far side of the lens. Incident ray traveling towards the focal point will refract and travel parallel to the principal axis. The third rule for both lenses: an incident ray traveling through the exact center of the lens will continue to travel in the same direction after refracting through the lens. If the incident ray will travel in the same direction after refracting through the lens. Ray diagrams redux. We can use ray diagrams to locate and describe the characteristics of an image. Step 1. Draw the incident rays parallel to the axis through the focuses and all through the center. This is the real, or this is the object. We must draw 3 rays. The first one parallel to the principal axis, like this. This is principal axis, and this is incident, first incident ray. It will be parallel. So, as we learned before, this will refract, pass through the focal point, and one will travel through center of lens, and this will change its direction. It will not refract. And the third one will pass through a focal point or focuses, or the focus of will pass through the focus of the lens and will refract. Yes, good. It will be refract parallel to the principal axis. Good. Second, step 2, draw the refracted ray according to the refraction rules. Third, locate the image. All point will focuses, or ray will focuses in this point. So this is will be, this is the image of the object. The image of object beyond 2f is far than twice of focal length. So the image will be smaller than the object, inverted between f and double f. It will locate it between f and double f. It's real. If the image of the object is at 2f, the image is. What happens if we put the object at a distance twice of focal length front of the lens? We will draw 2 rays. Yes, the same. If we put the third ray through center of focal, it will be pointed also in this point. Now, first one reflects through the focal point, and next one will parallel to the axis, principal axis, and make image. What is the characteristic of the image? At the first, we can see that have the same size and inverted at double f, and this ray diagram for object is located at double f. If the object is between double f and f, the image is yes. If we change the position of the object between 2f and f, I will have object, but characteristic of object is different. At first, it's larger and inverted. Beyond double F, it will be faster than double F and rare. If the object is at F, an image is not forming. Why? Because the refracted ray, it will be parallel. So I will have image if only the refracted ray are, yes, cross a certain point, but they pass parallel, so willing to cross, so the image willing to constrain. If the object is between F and the lens, the image is, so if we put the object between F and the lens, now in last one we have a parallel ray, but in this situation we have diverging ray. So the image will be larger because it will be at the same side of the object, far than double F, upright, yes, have the same direction, farther from the lens, and virtual, not real, it's virtual. For diverging lens, the image is always smaller, upright, closer to the lens, and virtual. As we see before, in diverging lens, we can do the same steps for drawing the image and have characteristic of the image for diverging lens. If we put the object far from double F, the constructed image or the image will be upright, smaller, and virtual. Why virtual? Because we have it from extended of reflected ray, like this dashed line. If we put the object between double F and F, I will have also smaller, yes, upright, and closer to the lens, and virtual. Also, if we put close the object to F, not on F, close to F, I will have smaller, upright, closer to lens, and virtual image. The linear magnification M is given by linear magnification. It means what happened to the image. It will be smaller, larger, like this. Magnification or linear magnification equal heights of image divided by heights of object. It can be shown that in all cases M equal distance of image from lens divided by distance of object from lens. So we can calculate linear magnification by two ways: height of image divided by height of object, or distance of image from lens by distance of object from lens. Power of lenses: the shorter the focal length of lens, the stronger it is. It means the more it converges or diverges a beam of light. We define the power P of a lens to be 1 over focal length of lens, where the focal length is measured in meters. P equal 1 over F.